Hi Bobcats! In this video we're going to see how changing the way that our balanced chemical equation is written can impact the numerical value for K. So formally stated, our objective is to manipulate equilibrium expressions based on changes to the chemical equation. Simple changes to the way that we write the balanced chemical equation result in changes to the expression for K, and that can result in changes to the numerical value for K. Let's look at what happens if we multiply all of the coefficients in a reaction by a constant. You might remember doing some of this type of thing back in Gen Chem 1 when you were doing thermodynamics. You might multiply all the coefficients by a constant as you were working on Hess's law type problems. So let's write the equilibrium constant expression for the process of creating ammonia, nitrogen plus 3 hydrogens in equilibrium with 2 ammonias. If we write the K expression, we have ammonia squared divided by nitrogen and divided by hydrogen cubed. I label this K1 as an indication that that's the basic expression for the equilibrium constant that we're going to keep coming back to. Now, let's imagine that for a Hess's law type problem, we needed to multiply all of the coefficients in this equation by a constant. So say we multiply them all by 2, and we now have 2 nitrogen plus 6 hydrogen in equilibrium with 4 ammonias. Well, if we go to write the equilibrium constant expression, the chemicals are the same, but the exponents are different now. We're going to have ammonia raised to the 4th power instead of squared, and nitrogen is now squared, and hydrogen's now to the 6th power. So basically, by doubling all of the coefficients, we doubled all of the exponents in the K expression. And so when we think about this mathematically, if all of the exponents were multiplied, that's like raising a power to a power. So I'm going to pull that 2 outside as a power that we're raising our original equilibrium constant to. And so the bottom line is that our new equilibrium constant expression, or our K2, is equal to our original equilibrium constant expression raised to the 2nd power. So multiplying all of our constants by 2, multiplying all of our coefficients by the constant 2 caused us to raise our equilibrium constant to the 2nd power. Bottom line, if you multiply all of the coefficients by a constant, raise K to that same constant. Let's see what happens when we reverse a reaction. So let's go back to our same original reaction and our same original K1, our equilibrium constant. And now let's flip this reaction around. And so let's make 2 ammonia the reactants and nitrogen and 3 hydrogens the product. If we write the equilibrium constant expression for this new version of the reaction, nitrogen and hydrogen have to be in the numerator and ammonia is going to be in the denominator. And again, we have to raise all of the values to the right value of the coefficient. So if we compare this new K2 to our original K1, they're reciprocals of each other. So this expression that we have right here is the reciprocal of what we had up top. Another way of saying reciprocal is that we're raising something to the -1 power. So our K2 in this case is equal to K1 raised to the -1. The bottom line this time is if you reverse a reaction, take the inverse or the reciprocal of K. I'm just going to bottom line this one. The textbook goes through a derivation. It shows an example of how you arrive at this. But the bottom line for this third branch is if you add 2 reactions together, the K for the net reaction is the product of the individual Ks. So you would take K for the first reaction and you would multiply it by K for the second reaction to get K for your net reaction. So let's look at a couple of examples of how we would use these processes of manipulating the equations and calculating a new value of K. So let's use as our starting point the dissociation of sulfurous acid, H2SO3 in equilibrium with H plus HSO3 minus, and that has an equilibrium constant of 1.7 times 10 to the minus 2. Let's first find K for the reverse of this reaction, H plus HSO3 minus in equilibrium with H2SO3. So we just took what were the products and moved those to the reactant side, and what was the reactant and moved that to the product side. When we reverse the reaction, we will take the reciprocal of our K. So we will take 1 over K, or 1 over 1.7 times 10 to the negative 2. So if I run that through my calculator, I'm going to take 1.7 EE negative 2, and I'm going to hit the reciprocal key. You could also type that in as 1 divided by 1.7 times 10 to the minus 2, and I get that for this reaction, our new value of K is equal to, oh, that got really sloppy. Sorry, I'm going to erase that. Okay, feel a little better about that. Let's just call this K for the reverse reaction. That's going to be 58.8. We only had 2 sig figs in our original number, so I probably really should just round that to 59. Now let's take a look at the reaction in part B. It says 3 sulfurous acids in equilibrium with 3 H pluses plus 3 HSO3 minuses. What happened to our original reaction to turn it into the reaction given here in part B? Well, it looks like we multiplied all of the coefficients by 3. If you multiply the coefficients by a constant, you have to take the K value and raise it to the power of that same constant. So for the reaction in part B, we'll take 1.7 times 10 to the minus 2 and raise that to the third power. Now in this calculator that I'm using at the moment, I'd enter 1.7 times 10 to the negative 2, and then I've got this y to the x key, and so I'll hit that, and then I'll hit a 3 to cube that number. And I'm going to flip that over into scientific notation, and the answer that I got was 4.9 times 10 to the negative 6. For the sake of comparison, because you're probably thinking, wait a minute, this seems familiar, but it's not quite right. Let's compare what we just did with the equilibrium constant to what happens with the thermodynamic values. Now in Gen Chem 1, you covered delta H's. That's the change in enthalpy for a reaction. In Gen Chem 2, later on this semester, we're going to cover delta S's and delta G's. So that's something yet to come. I'm just putting it here for completion. When you're studying for the final, this will make perfect sense. So if we multiply all of the coefficients by a constant, for the thermo values like delta H, we're going to multiply the value of delta H by that same constant. But not so with equilibrium. We're going to raise the equilibrium constant to the power of that constant that we multiplied all of the coefficients by. If you reverse a reaction in thermodynamics, we're going to change the sign. So an endothermic reaction becomes exothermic. But with the equilibrium constant, we're going to take the reciprocal of K if we reverse the reaction. And then in thermo, if we add 2 reactions together, we also add their delta H values, but not so with Ks, with these equilibrium constants. If we add 2 reactions together, we're going to multiply their Ks to get the K for the overall reaction. At the end of the semester, the last chapter we cover will be electrochemistry, and we're going to add one more column to this table where we see how manipulating the equation affects the standard potential for each reaction. And the last thing I want to do for this section is to take a look at the size or the magnitude of K. If we look at the expression for the equilibrium constant, it's products over reactants, and they're all raised to their coefficients. So products are in the top, reactants are in the bottom. So if, when we're at equilibrium, we have a whole lot more of the products than we do of the reactants, the numerator of this expression will be much bigger than the denominator, and that's going to make K a really big number. So one of the things that we say is that if K is much bigger than 1, it's a big number, the equilibrium position favors the products. That means we have more products than reactants when we're at equilibrium. So big values of K mean lots of products at equilibrium. We could also make the opposite argument. Let's say we didn't have very many products at equilibrium, but we had a whole lot of reactants. That means our numerator is small and our denominator is big. And so K is going to be a really small number. So we'll say if K is much smaller than 1, that equilibrium position favors the reactants. So the bottom line when it comes to K is that size matters. Our main objective for this video is to see how the equilibrium constant changes if we change the way we write the balanced chemical equation. We saw that if we multiply all of the coefficients times a constant, we'll raise the value of K to that same constant. If we reverse a reaction, we'll take the reciprocal of the constant. And if we add reactions together, we multiply their Ks to get the K for the net reaction. Also, we saw that equilibrium constant values that are really big mean that we have a lot more products than reactants, and equilibrium constants that are very small, much smaller than 1, mean that we have many more reactants than products at equilibrium.